Redox titration. The redox titration is an example of a direct contact reaction. The conditions of the titration are reaction complete, fast, and unique. Consider the reaction between Rad1 and OX2. So we have two couples involved, OX1, Rad1, and OX2, Rad2, and E of the couple OX2, Rad2 is greater than OX1, Rad1, since the OX2 is transformed to Rad2, and this is a reduction. To note that the electrochemical reaction is always spontaneous if E of the reaction is positive or delta G is negative. And if this reaction is spontaneous, it should be exothermic. So delta H is negative. It releases energy as electricity in the electrochemical cell, and it releases heat in the direct contact. The potential of the couple 1 is given by the expression according to Nernst equation E1 equal E01 plus 0.0592 divided by N log concentration OX1 divided by Rad1, and E2 equal E02 plus 0.0592 divided by N prime log OX2 and Rad2. To note that E1 and E2 are variable in course of the reaction, since the concentration of Rad1, OX2, OX1, and Rad2 will be changed in this reaction. So at T equals 0, E of the reaction equal E reduction minus E oxidation. So E of the reaction equal E2 minus E1, and at T equals 0, E2 is in its maximum value and E1 is in its lowest value. So E of the reaction at T equals 0 is maximum. When the reaction proceeds, the concentration of Rad1 and OX2 will decrease, that of OX1 and Rad2 will increase. So in course of the reaction, concentration of Rad1 decrease, OX1 concentration increase, so E1 will increase in course of the reaction. And the concentration of OX2 will decrease, that of Rad2 will increase, so E2, which is equal to E02 plus 0.0592 N prime log Ox divided by Rad, will decrease. That means E of the reaction is maximum at T equals 0. And in course of the reaction, since E2 will decrease and E1 will increase, so E of the reaction will decrease. At equilibrium, when the reaction reaches the equilibrium, so E of the reaction is equal to 0, and in this case, the potential of the couples 1 and 2 are equal at equilibrium. To note that when the reaction reaches the equilibrium, any stress on it will shift the reaction in direction 1 or in direction 2 according to Le Chatelier principle. For example, suppose the temperature will increase. Since our reaction is exothermic in direction 1, so it's endothermic in direction 2. When the temperature increases, we know that the equilibrium will shift in the direction endo, so the equilibrium will shift in direction 2. Therefore, the cell will function for a while in direction 1 to reach another new equilibrium. Consider the redox titration example. The titration of 100 milliliters of SN2 plus concentration 0.01 molar by a solution of Fe3 plus 0.02 molar. First of all, we have to know what is the reaction taking place. So we have to do increasing order of E and then apply the gamma rule. If we want to calculate E of FeC plus Fe2 plus, we have only the concentration of FeC plus, but Fe2 plus is unknown. So according to Nernst equation, E of the couple FeC plus Fe2 plus could not be calculated. By the same way, SN4 plus is unknown. We have only the concentration of SN2 plus. So E of the couple SN4 plus SN2 plus could not be calculated also. So in this case, instead of the potential E, we put increasing order of the potential E0, and E0 FeC plus Fe2 plus equals 0.77, E0 SN4 plus SN2 plus equals 0.14 volt. Then we determine the species present. The species present are Fe3 plus and SN2 plus. So we have a reaction according to gamma rule. And the reaction is Fe3 plus SN2 plus gives 2Fe2 plus SN4 plus. And we write also the half reactions. K for this reaction is given by the relation 10 to the power n prime E0 of the cell divided by 0.0592. E0 of the cell is equal E0 reduction minus E0 oxidation equals 0.77 minus 0.14, so it's equal 0.63, n equal 1 and n prime equal 2. So the value of K by calculation is equal 1.91 times 10 to the power 21. We can say the value of K is very high, so we can consider this reaction complete. In this problem of titration, when we add Fe3 plus to SN2 plus, the concentration of the reactants and the concentration of the product will be changed. So we have to calculate the potential of the solution after the additions of Fe3 plus and the specific additions V equal 10, 50, 100, and 150 milliliters. So calculate the potential of the solution for the addition of 10 milliliter of Fe3 plus. In any titration problem, the first step is the calculation of the equivalence point VE. According to the stoichiometric ratio of this reaction, the number of moles of Fe3 plus reacted divided by 2 equal number of moles of SN2 plus reacted divided by 1. At equivalence, all SN2 plus has been reacted, so the number of SN2 plus initial divided by 1 equal the number of moles of Fe3 plus added at equivalence divided by 2. So Fe3 plus times VE divided by 2 equal SN2 plus initial times V0 divided by 1, and therefore we calculate the equivalence point, which is 100 ml. So the 10 milliliter of Fe3 plus added will react completely since this volume is before the equivalence point. So Fe3 plus is the limiting reagent and the reaction between FEC plus and SN2 plus will proceed till the equilibrium. At equilibrium, E of the reaction equals 0, E of the solution is equal E of couple FEC plus Fe2 plus equal E of the couple SN4 plus SN2 plus. So adding 10 ml of FE3 plus, initially we have SN2 plus 10 times 10 minus 4 mole. FE3 plus added is 10 times 10 minus 3 times the concentration of FE3 plus initial. So we have 2 10 minus 4 mole. FE3 plus is limiting, will react completely. We have at T equal infinity 9 times 10 minus 4 mole of SN2 plus remained. Pay attention that FEC plus reacted divided by 2 equal SN2 plus divided by 1. So we have 1 times 10 minus 4 mole of SN2 plus disappear. So we have 9 times 10 minus 4 mole remained. And we have 2 10 minus 4 mole of Fe2 plus formed and 10 minus 4 mole of SN4 plus formed. Then the reaction proceed a little bit in direction 2. So we have 10 minus 4 minus 1 epsilon, 2 10 minus 4 minus 2 epsilon, 10 times 10 minus 4 plus epsilon, and we have 2 epsilon of FEC plus formed. Since epsilon is negligible with respect to 2 10 minus 4 and 2 10 minus 4 and to 9 10 minus 4, we can cancel epsilon. So at equilibrium, SN2 plus is equal to the number of mole formed at equilibrium divided by V total, which is 110 ml. So SN2 plus at equilibrium equal 8.181 times 10 minus 3. SN4 plus at equilibrium equal 9.09 10 minus 4, and Fe2 plus equal 1.818 times 10 minus 3 molar. Why I calculate the concentration of all the species at equilibrium? Because the objective is to calculate E of the solution, which is equal to E of couple 1 FEC plus Fe2 plus, or E of the couple 2 SN4 plus SN2 plus. So we have to know the concentrations of all species to apply Nernst equation. So now we have SN2 plus, SN4 plus, which are known, so we can apply directly Nernst on this couple. If we want to apply Nernst on the couple FEC plus Fe2 plus, we need to calculate FEC plus, so we need to calculate epsilon. At equilibrium, the equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants according to the stoichiometry, and the concentrations are at equilibrium. So K equal Fe2 plus square times SN4 plus divided by FEC plus square times SN2 plus. We calculated SN2 plus previously, SN4 plus, and Fe2 plus, so we can calculate the concentration of FEC plus, which is equal to 1.39 times 10 minus 14. As we said, when the reaction between FEC plus and SN2 plus proceed, this reaction will reach the equilibrium. At equilibrium, E of the reaction equals 0, and E of the solution is equal to E couple 1 or E couple 2. So now we will apply Nernst equation on couple 1 and on couple 2, and we have to find the same answer of E of the solution. So applying Nernst equation on couple 1, E1 equal E01 plus 0.0592 divided by n log x divided by rad. E1 equal E0 of FEC plus Fe2 plus 0.77 plus 0.0592 divided by the number of electron exchanged in the couple 1 log concentration of the ox divided by the rad. So E1 equal 0.11 volt. We apply also the Nernst equation on the couple 2 SN4 plus SN2 plus. E2 equals 0.14 plus 0.0592 divided by 2 log ox concentration divided by the rad, and we should obtain the same answer, which is equal 0.11 volt. So as a conclusion, addition 10 milliliter of Fe3 plus on a solution of SN2 plus will proceed a complete reaction between Fe3 plus and SN2 plus. This 10 milliliter of Fe3 plus will disappear completely since the volume added is before the equivalence point. The reaction will proceed till the equilibrium, and at equilibrium E of the reaction equals 0 and E of the solution equal E couple 1 or equal E couple 2 equal 0.11 volt. Was it necessary to work or to calculate E of the solution on the two couples? Since the 10 milliliter added is before the equivalence and Fe3 plus will be limiting, so it's easier to work only on the couple SN4 plus and SN2 plus to avoid, for example, the calculation of Fe3 plus. Calculate the potential of the solution after the addition of 50 milliliter of Fe3 plus. The equivalence point is equal to 100 milliliter. So 50 milliliter is the half equivalence point. That means the addition of 50 ml Fe3 plus will disappear completely and will transform the half of the initial SN2 plus to SN4 plus. The reaction will proceed till the equilibrium, and to note that the equilibrium we reach after addition of 50 ml is different from the equilibrium from the previous equilibrium where the volume is equal 10 ml of Fe3 plus added. So at the new equilibrium, the E of the reaction is equal to 0 and E of the solution is equal to E of couple 1 Fe3 plus Fe2 plus at half equivalence, or equal E of couple 2 SN4 plus SN2 plus at half equivalence. But since the volume added is before the equivalence, so it's easier to work on the couple SN4 plus SN2 plus to avoid additional calculations of Fe3 plus and Fe2 plus. So we apply Nernst equation on couple 2, E2 equal E02 plus 0.0592 divided by 2 log SN4 plus divided by the concentration of SN2 plus at half equivalence, and these concentrations are equal. So in this case, the potential of the solution at half equivalence is equal to E02 equal 0.14 volt. Calculate the potential of the solution at 100 ml, which is the equivalence point. When we add 100 ml of Fe3 plus, the reaction between Fe3 plus and SN2 plus is complete, and all these quantities, initial quantities, will disappear of Fe3 plus and SN2 plus. So we construct the table of conversion at t equals 0. We have 10 minus 4 mole. We have SN2 plus 10 times 10 minus 4. The reaction will proceed till equilibrium at t equal infinity. So no Fe3 plus and SN2 plus remained. We have formation of 20 times 10 minus 4 mole of Fe2 plus and 10 times 10 minus 4 mole of SN2 plus. the reaction will proceed therefore in direction 2, but this reaction in direction 2 is highly limited. So at the new equilibrium, we have 20 times 10 minus 4 minus 2 epsilon, 10 times 10 minus 4 minus epsilon, epsilon, and 2 epsilon. So by this way, we can calculate epsilon according to the equilibrium constant K. And after we find the value of epsilon, we know therefore the concentration Sn2 plus, Sn4 plus in the solution at equivalence. So we can apply Nernst equation on the couple Sn4 plus, Sn2 plus. And also we know FeC plus and Fe2 plus at equilibrium. We can apply Nernst equation on this couple and we should obtain the same answer. So now we have to calculate, in this case, epsilon. At equilibrium, K equal the concentration of the product divided by the reactant according to the stoichiometry. We can neglect epsilon with respect to 20 10 minus 4 and epsilon with respect to 10 times 10 minus 4, since the reaction in direction 2 is highly limited. And we calculate therefore the value of epsilon. Epsilon is equal 8.059 times 10 minus 11. So the concentrations at V equivalence are the following, and now we can apply Nernst equation on each couple. Applying Nernst equation on couple 1, E1 equal E01 plus 0.0592 divided by 1 log concentrations FeC plus divided by Fe2 plus at V equivalence, so equal 0.77, and we put the concentrations by their values, and we find E of the solution equal E couple 1 equal 0.35 volt. By the same way, if we want to apply E on couple 2, we should obtain the same answer, E2 equal 0.35 volt. In this type of exercise, we apply E on one couple. It's not necessary to apply E on the second couple. We have another method to calculate E of the solution after the addition of 100 ml of FeC plus, so at equivalence. At V equivalence, E of the solution equal E couple 1 equal E01 plus 0.0592 divided by 1 log FeC plus divided by Fe2 plus concentration at equivalence, or E of the solution equal E couple 2 equal E02 plus 0.0592 divided by 2 log Sn4 plus divided by Sn2 plus concentration at V equivalence. On the expression of the couple 2, multiply by 2, so we have 2E equal 2E02 plus 0.0592 log Sn4 plus divided by Sn2 plus concentrations. Add the two expressions of the potential of the solution E, so we obtain E plus 2E, 3E, equal E01 plus 0.0592 divided by 1 log FeC plus divided by Fe2 plus 2E02 plus 0.0592 log Sn4 plus divided by Sn2 plus. So 3E equal E01 plus 2E02 plus 0.0592 common factor log FeC plus times Sn4 plus divided by Fe2 plus times Sn2 plus at V equivalence. And we know at equivalence, the concentration of Fe3 plus equal 2 times concentration of Sn2 plus, and that of Fe2 plus equal 2 times Sn4 plus. So the expression 3E equal E01 plus 2E02 plus 0.0592 log expression, all this expression, FeC plus concentrations and Fe2 plus, Sn4 plus, Sn2 plus become equal to 1, since FeC plus equal 2SN2 plus and Fe2 plus equal 2SN4 plus. So log 1 equals 0, and in this case we have 3E equal E01 plus 2E02, and therefore E equal 0.35 volt. This method is easier than the previous, since we did not do calculations of the concentrations. We applied directly E as a function of E01 and E02. So as a general rule, at equivalence, E of the solution equal the number of electron exchanged in couple 1 times E01 plus the number of electron exchanged in couple 2 times E02 divided by N1 plus N2, and this relation can be applied directly without proof. Calculate the electrode potential or the potential of the solution after the addition of 150 milliliter. This volume is after equivalence. So after equivalence, it's easier to use the couple FeC plus Fe2 plus, since Fe2 plus is formed at V equivalence and FeC plus will be in excess. So at V equivalence, we calculated the number of moles of all species, and the number of mole of Fe2 plus is equal 20 times 10 minus 4, and after V equivalence, no new Fe2 plus ions will be formed, since the reaction is stopped. No reaction after V equivalence, and we will have Fe3 plus in excess. So the potential of the solution after equivalence is equal to the potential of couple 1 equals E01 plus 0.0592 divided by 1 log FeC plus at the volume V, 100 ml, divided by the concentration of Fe2 plus at this volume. So V equal 150 ml is divided into two parts. 100 ml of this volume is responsible for the complete transformation of SN2 plus initial by FeC plus to Fe2 plus and SN4 plus, and we will have 50 ml in excess. So the number of mole of FeC plus added is equal to the concentration of FeC plus times the volume equal 310 minus 3 mole. The number of mole of FeC plus consumed till the equilibrium is equal to the concentration of FeC plus initial times the V equivalence is equal 2 times 10 minus 3 mole. So the number of mole of FeC plus in excess is equal number of mole of FeC plus initial added minus the number of mole of FeC plus reacted till the equivalence. So the number of mole of FeC plus in excess equal 10 minus 3 mole. Therefore, we can calculate the concentration of FeC plus in excess, which is equal to the number of mole divided by V total, so equal 0.004 molar. So after the addition of 100 ml, we have number of mole of FeC plus equal 10 minus 3. The concentration of FeC plus equals 0.04 molar, and the number of mole of Fe2 plus that is formed at equivalence is equal 20 10 minus 4 or 2 10 minus 3 mole, and the concentration of Fe2 plus equals 0.008 molar. So we can apply Nernst equation on the couple FeC plus Fe2 plus, E equal E01 plus 0.0592 divided by 1 log FeC plus divided by Fe2 plus, and therefore E is equal to 0.76 volt. So now we draw E of the solution, or the electrode potential, as a function of the volume of Fe3 plus added for 50 ml. For 10 ml Fe3 plus, the potential of the solution equals 0.11. For 50 ml, the potential of the solution 0.14. For 1 ml, the equivalence point, the potential equals 0.35. And for 150 ml, the potential of the solution is equal 0.76. So we obtain a curve which is identical in shape as the variation of the pH as a function of the volume added in the chapter acid base. Redox indicators. Redox indicator is a substance used during the titration redox. It changes its color when it passes from its oxidized to its reduced state. For example, ox plus an electron that give red, so E equal E0 plus 0.0592 divided by n log concentration ox divided by the concentration of the red. As with the acid-base indicator, the color of ox will be observed when the concentration of ox is greater at least 10 times than that of red, and the color of red will be observed when the concentration of red is greater or equal 10 times the concentration of ox. So the color change at equivalence will occur over the range E equal E0 plus minus 0.0592 divided by n in volt, where n is the number of electrons exchanged in the indicator have reaction. Or in other words, what is the best redox indicator that can be used? The best is that where E of the solution or E of the system at equivalence belong to the range E0 of the couple minus 0.0592 divided by n, and E0 of the couple plus 0.0592 divided by n. This is identical to the best indicator used in the pH titration. The best indicator used in the pH titration is that where pH at equivalence belong to pKa minus 1 and pKa plus 1 of the couple. The last slide is about the electrodes used in the potentiometer or in the redox titration. There are different types of electrodes depending on the nature of the metallic conductor and the oxidant, the reductant species involved in the half cell. So one of the common electrodes used is the standard calomel electrode known as SCE. The SCE is composed of mercurous chloride, Hg2Cl2 calomel, in contact with mercury metal, either as a pool or as a paste with calomel. These components are layered under a saturated solution of potassium chloride or surrounded by the saturated KCl solution. This is called a double junction arrangement. A platinum wire is allowed to contact to the external circuit. Hg2Cl2 plus 2 electrons give 2Hg liquid plus 2Cl minus, and the potential is equal 0.241 volt with respect to the He at 25 degree. This slide is only to know or to read the type of electrodes used in redox and all these informations are only to read.